Okay, so the deep dive.
That thumbs up was me, not Santiago.
Oh, god damn it.
Okay. Santiago said on Zulip. It's fine. Let's go.
Okay, got it.
Okay. So today's deep dive is about the way we interact with the trade solver in Rustc. And I'm not going to explain everything, so ideally you already are kind of familiar with some of the parts already. This is also with a focus on the differences between the new and the old solver. So the core API to prove goals in the type system, those don't change. It's going to remain the obligation context. So whenever you need to handle some predicates, you need to prove something, you either use an existing obligation context or create one yourself. And you already have one in the function context, or like performance checking already has an obligation context for you. So yeah, but we still go for obligation context. We still just do register obligation and then call selective okay. Call select where possible or select all or error. So that API hasn't changed. And under the hood, we just delegate to a, where is new? Yeah, exactly. We just delegate to a separate trade engine implementation, which differ between the old and the new solver. So we go for the obligation context, and there are, in the old solver, there are some subtle differences between using evaluate or using the fulfillment context. For example, what is it? Must hold. That doesn't work how I thought. Was it that one? Was it a different one? Yeah, okay. Can't find that it's written down the method name. In the old solver, just because evaluate succeeds doesn't mean that fulfillment will succeed. So we sometimes are careful and like do both or have to deal with mismatches. Whereas in the new solver, those are not separate concepts. So you actually can just always use the application context, and you should also always use an application context. So
I'll add to that fulfillment in the new solver literally just uses the obligation context. So you're not saving any operations or you're not saving any work by checking whether a predicate may hold first before like putting it in an obligation context. I even tested it perf-wise to see if calling the solver like in a raw way by using the eval context directly would save any perf, and it didn't. One other thing I'll note is that evaluation in the old trade solver has some subtlety around overflowing in a non-fatal way that the new trade solver doesn't. So sometimes we have calls to evaluate in the old solver that prevent ICEs, or not ICEs, but like crashes in the compiler, fatal errors in the compiler that we don't need anymore. So basically, you should never need to call predicate must hold modular regions unless you are implementing diagnostics code and you want to have like a quicker way of checking whether something holds. But even then, often it turns out that you write code that is simple and then you need to upgrade it into an obligation context to do something more interesting, like as soon as you want to do non-trivial amount of trait checking. So often it's just easier to make an obligation context from the get-go.
So one important concept we've introduced while working on the trade solver, and it also impacts the old trade solver, but it's been part of our implementation work, is that we now more explicitly keep track of the current typing mode, which is pretty much replace the existing reveal flag, and it changes the trade solver behavior in some cases. So we've got different typing modes depending on which part of the compiler you're in. For example, going through them, we have the coherence mode, which is used during overlap checking and coherence. And that one needs to deal with unknowable impulse and also just has to be more careful with failing to prove something. So that one is treated separately and has small differences in the solver. And then we've got 3 modes during the actual analysis and type checking. We've got the first one used during your type check and performance checking. And then we've also got a mode used after your type check until we've done borrow checking, which is the borrow check mode. And then we've got the post-borrow check analysis. And these are exactly the same, except that they treat opaque types differently, and that we stall looking into the generator witness of generators local to the current body to avoid cycle errors in analysis. But this is only impacting opaque types, and the general idea is your type check with analysis. Then, if you're inside of a body but haven't borrow checked yet, use the borrow check typing mode. And then after borrow check, for example, in lins, we can use the post borrow check analysis mode. And finally, during cogen, we use post analysis, which is was previously reveal all. And these ideally shouldn't be added for bad reasons, as in adding new ones makes the type system more complex to reason about. It makes caching worse, and just in general, it's already kind of sad that we've got 5 of them and might have more in the future, but we shouldn't have too many because it makes reasoning about the type system harder. And if you're unsure what typing mode to use, in pretty much all cases, you have the correct typing env available to you, because the typing mode is stored in the inference context. So whenever you already have an inference context, you just have the right typing mode by default. And in cases where you're not sure where you don't have an inference context yet and you have to create one, most of the time you already have the typing env, which stores the current word bounds and the typing mode you should use. So pretty much, if there's any case where you need to create your own typing mode, probably ask in the t-types Zolib stream about it, because generally it should already be available somewhere. And one other place where we store them is in mirror bodies. So if we look at a mirror body, this body stores its current mirror phase, and I think, where is it? There's some way to get the typing env from the mirror body, and I don't know where it is. But yeah, you can also get the right typing mode from
method on body.
It's a method on body?
Yeah,
cool.
So I think it's either in mirror mod or in mirror syntax. So if you search in the file you're in, you might be able to find it.
Yeah, exactly. It's a method on body.
Because as we go through different mirror phases, we also go through different kind of reveal modes for opaques. That's reflected in the passes we apply to them, and also what the optimizations are allowed to do with the types that we have. So when you're implementing a mirror optimization, typically, unless you're implementing an optimization that's responsible for changing the typing env of the body, like the reveal opaques pass, you can typically just call body.typingenv if you need to create an inference context to do some type checking, but to do an optimization or something like that. So, and this is also true for lint passes. So the late lint context, it's typically called CX when you're implementing one, also has a typing env function. And basically a lot of, when you're, as a user, when you need to create an inference context, there's typically a typing env function in whatever associated context you're in, to help you not have to, well, to help us maintaining the type system so we don't have to change a bunch of call sites because they're consolidated into one, and to help you because you don't have to think about what typing of to use, because using the right typing of will, I mean, it can be anything from soundness critical to at least creating ICEs and causing weird diagnostics and things like that.
Yeah. Okay. The biggest change between the old and the new solver is the way normalization works, where in the old solver, you tended to always eagerly normalize, which is why in what's good case where you can see that. Okay, no idea. Anyways, in the
There's a lot
old
of
solver,
normalization in compare method predicate entailment, for example. We take the predicates and then we normalize the predicates, then we take the normalized predicates and then we register them and stuff like that.
yeah, exactly. So
yeah,
always in the for the odd solver, before you register an application, you need to explicitly normalize it. Before you equate types, you need to explicitly normalize them. And it's very subtle, but there are also just a few cases where it's currently either we just don't normalize, even though we should, or it's insufficient around higher rank types especially. So whenever you instantiate a binder, in theory, you would need to normalize again afterwards to deal with ambiguous higher rank aliases. But that's difficult to do. So yeah, you currently pretty much have to call normalize everywhere. And that's hard. People forget it. It results in weird bugs where things don't work even though they should. So that will no longer be the case in the new solver. Relating types can now deal with unnormalized types. So you don't need to call normalize before before you relate any types. So before you call it a queue or sub. And also as input to the trait solver before registering obligations, you also don't have to normalize anymore. And I think that's the biggest change with the new solver, that you just don't need to normalize everywhere. We do need to explicitly normalize in one case, however, and that is before you match on the tie kind. So if you do something based on looking at the actual tie kind, for example, here we check that whether A is the never type, that needs to make sure that we handle the case correctly where A started out as an associated type or an alias. Because if it's an alias, we don't know whether it's never. So what we do before calling cors is somewhere, exactly, is that we try structurally resolve. And that method looks at the type. If that type is an alias type, it normalizes that as much as possible and then returns it. So you generally don't have to normalize except when you actually match on the type kind, in which case you have to make sure that you call try structurally resolve. Ideally, as close to the match on the kind as possible to make sure that, well, try structurally resolve also does select a possible call to make inference progress. So if you constrain some stuff and then match, you might miss that information. But yes, general, before you match on the tie kind, or same for constants, call try structurally resolve. And this holds in general. So in the new solver, we no longer assume that types are normalized everywhere, even though as a side effect, it kind of sometimes happens, because when during generalization, which when we equate some type with an inference variable, we first we set the inference variable not equal to the type itself, but we first generalize that type, and that does actually replace associative types with inference variables. So like as a side effect of that, you kind of end up with normalized types in a lot of places, but it's still good form and sometimes required to try structurally resolve before matching on the type.
I wanted to note also that
Yes.
tristructure resolve only normalizes the outermost type in a type. So you can have like a struct with like args, and those args won't be normalized by tristructure resolve. So LCNR, when they said that you tristructure resolve before you call like dot kind on a type, that's so the match that we do on the tie kind is basically reporting the most accurate type that you can at that point. What it won't do is it won't normalize all the args inside of an ADT if you match on that ADT and then recurse. You'll have to call tristructure normalize again on the next match that you do, either when you recurse or you do another match or whatever. So that's basically the one thing you have to keep in mind, is that normalization in the old solver typically normalizes the type deeply, and tristructure resolve will normalize the type shallowly, or only the outermost type in that case, which is sufficient, obviously, for calling something like dot kind, which is where the overwhelming amount of normalization that happens in, at least in type check, is because it wants to match on the tie kind of the thing that's being called. Because, like, for example, if we're doing an index operator or a dot operator to access a field, we need to access the outermost tie kind to see if it's an ADT, to do, whatever, to see if it's a ref, to do auto deref. So that's one thing that you have to keep in mind, is basically, if you see a dot normalized call, you kind of have to conceptually understand what that normalize is trying to achieve, whether it's trying to achieve like a shallow normalization or a deep normalization. That's it.
So yes, so that you need to explicitly normalize the formatting of kind. There is one exception, or well, two-ish, that at the end of here type check, we explicitly deeply normalize all types inside of the body. So in the write-back results, everything is normalized, and that also applies to the mirror body then. So if you're in a mirror body, like all the types you can access directly, those will already be fully normalized. So in general, even when you match on the tie kind during mere borrow check or some mere analysis, you don't need to normalize there. However, if you look at the field of a struct, as in you do something that is non-structural, going from an ADT to one of its fields, then you will need to normalize again. But the mirror body itself will be fully normalized. That is just because it makes our life easier. I don't think it's required for it's not required for anything. It just means we need to have fewer tristructurally resolved calls everywhere else. And that also doesn't apply the moment you instantiate mirror bodies. So if during Cogen you instantiate a mirror body with generic arguments, in that case you also have to renormalize everything again. So
that should happen automatically with the dot instantiate mirror and normalize erasing regions. There's like a helper function that I think CodeGen uses ubiquitously to substitute the body with its instance args, and that will do it automatically. So users shouldn't have to worry about normalizing things in CodeGen if they're using the right instantiate functions already, and they should be, because it wouldn't work otherwise in the old trait solver. And CodeGen doesn't really make its own inference context and normalizes things manually. So
yeah. The way we actually explicitly deeply normalize and write back is via deeply normalize. So let's go to engine. By the function deeply normalize, which is very similar to just normalizing the out solver, and that it fully recurs into the types and just normalizes everything as much as it can, except that if something is ambiguous during normalization, deeply normalize errors, whereas the out solver took the alias, replaced it with an info var, and delayed the normalization until later. The reason we don't allow ambiguous normalization in deeply normalize is that we can't support it for higher rank aliases. So with the old implementation, if normalize encounters an ambiguous associate type which references some higher rank region, that alias just stays there and then later gets treated as rigid because we assume that it's normalized, even though it's not, because we kept it in there. And that is subtle. It can cause type mismatches in the mirror. Like there are quite a few very subtle bugs due to this. So the way we avoid this is by deeply normalize just emitting a hard error if it encounters any ambiguity. So you should only use it once you finished with inference, or don't do any inference at all at that stage. And most of the time, you just also don't want to use it at all. So deeply normalize is used in a few places, for example, to write back, because it makes a lot of things easier afterwards. But you generally only need to use structurally normalize or structurally normalize instead of deeply normalizing type. So yes, deeply normalize. Be careful when you use it, but that's what we use during writeback. And there's one thing deeply normalized and structurally normalized don't cover by themselves, which is diagnostics want fully normalized types, just so that we can print the best thing for users. And that should be deeply normalized, but it also shouldn't error if there's any ambiguity. So now we don't have a function here. There's this wonderful function called deeply normalized for diagnostics. And we use that to deeply normalize things while allowing for ambiguity in error messages. But as the name already states, it should only be used for error messages. So yeah, to deeply normalize, use deeply normalize. And you can also use normalize erasing regions if you don't care about region information or type inference. And normalize erasing region, as it does in the out solver, just continues to fully normalize, to fully deeply normalize the type. So normalize erasing regions still behaves the same as it did before. And that's all I've got for normalization. I'm not sure if Michael has anything more to say.
Nope, I think that's basically it. I think overwhelmingly, calls to normalization that happened in the old solver, that if you're implementing code like type checking for a new expression, just doesn't need to happen. Because most normalization happens just to normalize a predicate before we register it, or to normalize a type before we equate it, and all that just happens auto magically. And yeah, just making sure that all .kind calls on types and consts, kinds, and stuff like that get normalized before they get matched on is important, or else it will lead to bugs where an unnormalized type will be treated like what we call a rigid alias in the trait solver, which is an unnormalizable associated type, or at least unnormalizable in the environment that it's in. Those bugs are they'll typically not lead to unsoundness, but just code that we expect to work doesn't work. It's the same class of bugs that we'd have if we weren't normalizing in the old trait solver, We, for example, didn't used to like support normalizing to or not normalizing, upcasting to a DIN super trait that had like unnormalized associated types in the super trait, because we were missing a normalized call in the solver. So a lot of those kind of just get implicitly fixed because we have better normalization in the new solver. But yeah, so from a user perspective, typically you either want to think, no, I don't need to normalize my types at all, or I need to structurally normalize because I'm going to immediately match on .kind, or call a function like LCNR showed, like .isNever, which is kind of morally equivalent to matching on the kind.
Yeah. So the final thing for today, at least the final thing on our list, is that we generally don't want people to look into the traits. Well, when using the trait solver, ideally, we never rely on implementation details of the trait solver. So its API is generally limited to, well, normalizing stuff or just proving that something holds. But there are a few cases where we actually do want to look into what the trait solver is doing. And we still need to support those and for backwards compatibility, because also that are just desirable. And the way this is done is via proof tree visitors, where the new trait solver has a different mode where it keeps track of what it did while proving a goal, and then you can implement the proof tree visitor trait to walk over a simplified version of what the trait solver did. And that works quite well. It has a few caveats where it means, one, it's just more expensive than simply using the trait solver via the normal trait solver API. The visitors themselves also don't have great caching, which is by default, we significantly limit the recursion depth to avoid hangs if there's exponential blowup. And also it leaks some details of how we assemble candidates. So yeah, it makes painting the trait solver harder going forward. So we would like to not see too many uses of that happy path where so requiring it, using it in a way that is required for code to compile isn't too great, but there are a few uses, and let's look at different ways we can do it. So a very impactful one is deducing the closure signature, where if we've got the following function and then call with this compiles, but it needs to eagerly know the type of X, and it does that by figuring out what the signature of the closure should be before we actually recurse into the closure during here type check. And it does this by looking at the state, looking at the currently pending obligations. And this, unfortunately, sometimes also needs to look at both nested obligations and super traits. So we actually need to figure out how the trait solver is proving stuff, because that is just not part. Because the new trait solver only keeps the root goal in the fulfillment context, whereas the old solver always figured out which input to use and then took the nested goals and made those ambiguous and stored them in the fulfillment context. So we depend on being able to access nested goals to figure out closure signatures. And whoops, I should close it. I should we need to access nested goals to figure out the closure signature. And the way we support this is via a proof tree visitor. So that, wait, that was stupid. This visitor walks through the currently ambiguous goals we have in our fulfillment context. And for each goal, it checks whether the self type is the inference variable. This closure, if you use it for closure signature inference, this closure will be equated to. And if so, it stores it in a list. And if not, it checks whether there's a unique way this ambiguous goal can be proven. So as an example, when checking whether a vector of an inference variable is clone, we definitely know that we're going to use the input clone for vec of t, where t is clone. And then this call here would recur into the nested inference variable implements clone goal. So yeah, that's what this solver does. It works over all ambiguous goals. And if there's a unique way we can prove them, it recurses into them. And that's what we use to figure out the signatures for closures. Then another proof tree visitor is the select visitor, which is nice, found it. I think is used in two cases. One, we just need it during codegen. So when we monomorphize some method call, like need to resolve the input it corresponds to by instance resolve. And instance resolve internally uses codegen select candidate, I think, something like that. And that then also needs to know how the trait solver is actually proving the trait bound corresponding to the method. So we use a select proof tree visitor and call it for, so if we want to resolve the instance of vec clone, we would use a select proof tree visitor to visit the vec of U32 clone trait goal. And that looks at all the ways we can prove this trait goal. And if there's a unique candidate, it returns that impl as, like, returns the def ID pretty much of that impl. It does some other stuff, but who cares about that? The select visitor is also used for unsized coercions, which actually wants to do a bit more than the selector in codegen, where it manually recurses into the goals for whether something can be unsized or not, to decide whether or not we are even going to try to unsize, because we have to decide that eagerly. So it does some interesting pseudo trait solving. And that also uses select and that proof tree visitor. And the final case is diagnostics. We've got one visitor during coherence, which is looking through all ambiguous goals to figure out whether that goal is only ambiguous because the trait drift is unknowable. And then we have the best obligation visitor, which you might know that if you do the following, back of anything that is not clone. I think everything's stripped, not clone. If you have the following code, here by default, the new solver would just report that vec of not clone does not implement clone. But actually, for diagnostics, we want to tell the user the most specific reason why this fails, which is that actually the only way you can prove that vec implements clone is if it's field implements clone. So the best application visitor walks into a failing or ambiguous goal in the trait solver, so failing predicate we have to prove, and searches for the best leaf obligation, which is like responsible for the failure, which in the new solver is something we now do explicitly, whereas in the old solver, that's just a side effect of the way the fulfillment/evaluation loop worked, where fulfillment would always just, for every trait goal, check whether there's a unique way to prove it, and if so, put the nested requirements into the fulfillment context. So that allowed the old solver to just automatically report that the problem is a not clone, doesn't implement clone. So yeah, and the new solver we do it manually, which also means we can adjust or like implement a proper heuristic for when we want to report nested obligations and when we don't. Because in the old solver, this is tied to the implementation, which means that there are a lot of cases where the diagnostics would be better if we didn't recurse into nested goals, which is why there's now a do not recommend attribute, which does exactly that, but explicitly. But given that we've now got an explicit proof tree visitor for this, we can now also change the defaults here to make the diagnostics better for everyone except instead of only for libraries which manually add those attributes where applicable. And yeah, this is, I think, the most involved proof tree visitor we have. But again, it's similar. When we visit a goal, we check whether it's the kind of goal we care about, and then do a bunch of stuff to decide whether or not to recurse into it, or whether to use it at the leaf goal. And yeah, so from what I can tell, proof tree visitors are kind of useful, just also for tools, where there are now tools which use the new trait solver to like have pretty IDE stuff, which is very cool. It's yeah, but we shouldn't use them on heavy path because they make our lives as trait solver developers harder. And this has been a lot of talking, but I'm done with my list. So yes, Michael, do you have anything to say?
I don't think so.
Cool.
I would maybe mention that if you go back to the trait for infer context proof tree X, or I think it's called proof tree infer context X, because just like what the API is for proof tree visitors, I kind of don't want green, but it's basically like all other visitors. But you call it on the infer context. You call infer context dot visit proof tree. You pass it the goal you want to visit in the visitor, and then you get your visitor called the implementation of visit proof tree, which will give you an expect goal, which is basically an obligation to prove something. The inspect goal has candidates because we have multiple ways of proving. We have multiple ways of proving a goal. We have some helper functions for basically cases like there's only one candidate for proving a goal. And LCNR is scrolling through all the internal
Yes, I'm trying to figure out what's FN visit. What are the code again?
Visit goal, yeah.
Yeah.
So, and this is like a visitor. It has the
So,
results kind of as a result associated type, which can either be unit or it can be control flow, depending on if your visitor is trying to look for something. But you basically it's kind of a mutual recursion of goals turn into candidates, and candidates have nested goals, and then goals have candidates, and candidates have nested goals. But how specifically you use a proof tree visitor is very dependent on what you actually want to do. The proof tree visitor that we use to look for obligations for closures is very different than the proof tree we use to do selection, because, for example, selecting just needs to know how we prove the outermost trait goal, versus something like coroutines or a proof tree visitor that I wrote yesterday to replace that manual funky loop for coerce unsized, needs to look at the full tree to basically make sure that we're proving something that we have decided through some heuristic that's grown over the last 10 years is worth coercing. So if maybe it's worthwhile in the future to do a deep dive on how to use proof tree visitors specifically, because how exactly they work is, well, it even depends on whether or not you're proving goals that hold versus they don't hold. For example, this nested obligations for self-tie visitor is only meant for goals that do hold, versus the diagnostics visitor that Elsinore had mentioned to kind of give us the best reason for why a root goal failed, is interested in proving goals that don't fail, which manifest themselves differently in the proof tree, because it has to make a distinction, for example, between a kind of proof subtrees that matter versus proof subtrees that don't matter. Because, for example, an impl that trivially doesn't hold is not interesting to look into, versus an impl that failed for a good reason, for some definition of good, is worth recursing into. So yeah, I think that's all that I have about proof trees. The API, I guess, to kind of go to conclusion before maybe Elsinore wants to do their own conclusion. The API for the trait solver is generally the same. We try pretty hard to make sure that users don't have to interact directly with the trait solver and have to do things that are different in the trait solver. This is because right now we have two trait solvers in the compiler, and we don't want users to have to do if next trait solver, then do this, otherwise do that. So I think right now the API is kind of hidden behind a lot of the existing APIs that you should be familiar with, like normalize erasing regions and obligation context that normalize, and predicate may hold. But I think as the new trait solver kind of becomes more ubiquitous, maybe these APIs will be simplified. But I think at least the goal for this talk is for people who are doing a little bit more interesting things with the trait solver are aware of the differences, so then they know how to both make their code resilient to the new trait solver in the future, and also just to kind of understand kind of the motivation for like why things exist in the way that they are, and how that ties into kind of the goals that we're trying to prove, or the goals we're trying to achieve with writing the new trait solver. So yeah, that's all I have to say.
Yeah, so this it was quite broad, I think. Yes, so if there are any questions, either ask now or just in general, especially when it comes to how things change with the new trait solver. Ask on Zulip. If you're too embarrassed to ask on Zulip, ask me in a private message. It is fine. Documentation is in a few areas good. For example, Boxy recently wrote a very good Rustc dev guide section on how normalization works in general. But of course, there are also still quite a few places where documentation can be improved. So yes, don't hesitate to ask if there's anything that's unclear which could use more information. So yes, any questions right now? All right. then that's the recording, I think. Very cool.
All right. Well, thanks for attending, y'all.
Yeah.
We'll have to think of timing for the next one and what we want to talk about for the next one. I think I will admit that I was supposed to do half of this talk, but I told Elsinore just to do all of it because it's a little early for me and I had some stuff to do this morning. But I think we'll try to hand off these talks between us two because talking about a lot of technical stuff is very exhausting. So, but if people have things that they specifically want to know, being as specific as possible for asking us is very useful because I think Elsinore and I both have the perspective of we don't know what people want to know about the new trait solver. So if people have things that they want to ask, please do ask. And if they want to know, if they want us to give y'all a free 1 hour lecture on something specific to the trait solver, we will. We just don't know what it needs to be. So so let us know.
Yes. And I personally think that so this one was like very broad, and I think like diving deeper into specific parts where looking at the code is more useful, or like actually checking out examples is something I would very much like to do. So if there are like concrete things, parts of the trait solver you want to know, please do ask. I want to talk more about the trait solver, and I don't know what to talk about. So yes, please do.